Every day, machine learning helps scientists search for new drug targets, classify diseases, and analyze enormous biological data sets. But what if some of the information the algorithm is learning from is actually misleading it? That question inspired our research. Machine learning is excellent at finding patterns in large data sets. The problem is that it treats every input feature equally, even though some measurements are much noisier than others. If those noisy measurements influence the algorithm, they can lead to biased predictions. In fields like drug discovery or genomics, that could mean overlooking meaningful biological patterns or even missing potential drug targets. So, how do you know whether an algorithm is actually making mistakes? We needed a data set where we already knew the correct answer. That's why we use global clusters. These are groups of stars that form together so they share nearly identical chemical compositions. Because we already know which stars belong together, we could tell whether the algorithm is clustering them correctly. We analyzed three clusters: M3 as our validation cluster, and M5 and M13 as independent cases. M3 allowed us to verify that our analysis pipeline worked before testing whether the same patterns appeared in M5 and M13. We use chemical abundance data from the APOGEE DR17 survey. For each cluster, we analyzed 19 chemical abundance measurements and radial velocity using the dimensional reduction algorithm UMAP to project the data into two dimensions. Next, we ranked each chemical abundance by its variability among confirmed cluster members. Finally, we removed the five most variable chemical abundance measurements and ran UMAP again. We then compared the baseline UMAP projection with the projection after removing the five noisiest features. As you could see, the confirmed cluster becomes noticeably tighter, meaning the known cluster members group together more consistently. There is less contamination from nearby field stars, and the separation is much clearer. Importantly, we observed the same pattern across all three global clusters, suggesting this wasn't unique to one dataset but a consistent effect of feature selection. Although we demonstrated this using the stars, the same machine learning techniques are widely used in drug discovery, genomics, and healthcare. If noisy features influence an algorithm, machine learning models may overlook meaningful biological patterns. That's why feature selection is so important. Our work shows that improving AI isn't always about designing more complex algorithms. Sometimes it's about making sure the algorithm is learning from the right information. By identifying and reducing the influence of noisy features, we can build machine learning models that are more reliable not only for astronomy, but also for drug discovery, genomics, and precision medicine.